Cool. Hello, everyone. My name is Chang. And so today we're going to talk about LLMs, vector search. We're going to, of course, talk a little bit about LanceDB. We're really going to start at sort of a high-level overview. I will try to show you a live demo. Hopefully it works, although it never does when I do talks. And then if we have time, we'll dig into some more interesting details about the low-level architecture of LanceDB and file format. But I guess first, you raise your hand if you've used ChatGPT. Okay, cool. So wait, hold on. Keep your hand up. Keep your hand up. Okay, keep your hand up if you built an application on an LLM or using some generative AI. Okay, still lots of hands. Keep your hand up if you know what an embedding is and if you've used vector databases before. Okay, nobody's hand went down. That's great. All right, and then, okay, last question. Keep your hand up if you know the difference between an HNSW and this index and an IVF PQ index. Okay, all right, okay, great. That was a great set of questions here. All right, so if you've used ChatGPT, you've sort of seen how sort of the hype around AI that's sort of taken the world by storm in the last 6 months, right? And really, I think LLMs are going to fundamentally change how we interact with computers. And as proof, I'm going to play this brief video.
AI, generative AI, generative AI, generative AI, AI is AI, 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 uses AI to bring AI, AI.
So this was a condensed video of Google I/O that just happened, and so we've all sort of seen the power of LLMs, right? But one thing that may not be clear to many of us is how do we actually interface our own data, or if you're building an application, how do you interface your customer and users' data with an LLM? And this is where vector search is critical, where is the interface between LLM and the data, where your generative AI agents or applications need memory, right? And so to solve this, we need to think about how to store the text, how to store the images, the embeddings, of course, and metadata and more, right? And how do you retrieve all that information? What does relevance actually mean in this context? And if you do it well, I guess to paraphrase Arthur C. Clarke, any sufficiently integrated first-party data in LLMs is indistinguishable from magic. Okay, so we've sort of convinced ourselves that we need vector search, but why do we need a different kind of database? Two kind of questions I get a lot. Why can't we just use, say, Elasticsearch or Postgres? Both have shipped vector indices recently. And the difference is both of those engines and sort of traditional databases are designed very differently. You can tack on a new vector index, but the design limitations make it very difficult to scale beyond sort of prototype scale. So if you take Elasticsearch, for example, the AWS made an OpenSearch fork, and they shipped HNSW indices, but still the architecture is based on Lucene. So how you create the cluster, how you do capacity planning, how you shard the data is all very dependent on that. And that is very incompatible with vector indices. Another question that I get is, well, why don't you just use face or annoy? And another show of hands, how many of you know what either face or annoy is or have used them? Okay, great. And so if you've used them, you know that they are vector indices. And they're very good at sort of indexing the data for ANN. Annoy has problems scaling. Fast is much more scalable. But there's a lot of work that you have to do to set up all the infrastructure around Phase to make it really work and connect to your app, right? So it's sort of the analogy is like when you use Postgres, you don't think, oh, why do I have to use Postgres? I can just use a Petri index instead, right? You never think that. It's because there's a lot of work that goes into organizing all the data. How do you fetch all of the, how do you map your vector index to your metadata and filter that to your image or text documents and things like that. All right, so those are sort of the reasons that motivated us to create LanceDB, which we kind of think about as like a SQLite or DuckDB for vector search. We're open source, so you can find us on GitHub. The core of it is written in Rust, and we have Python and JavaScript bindings. If you're in Python, which chances are good here, you can just pip install LanceDB, runs a process, there's no server required, your private data stays private. So LanceDB can, by default, stores data locally on your SSD. That's the fastest option. We can also connect natively to S3 or Google Cloud Buckets, and there's no sort of real difference other than the URL. Of course, latency is much higher from object storage. LanceDB is also the only vector database that I'm calling truly multimodal, because it's the only vector database where you can store text and images and point clouds along with your embeddings and metadata, and you can query it and fetch it all together. And it's also the only one where the querying is also truly multimodal. So you can, I just added full text search index to LanceDB. You can also run OLAP SQL queries on top of that data and filter that data sort of in conjunction with your in search and full text search. And the SQL support is done right now through DuckDB. And lastly, LanceDB is highly optimized. So we spent a lot of effort optimizing the Rust core. So two things that I think are really important here. One is the index is disk-based. We have both our own disk-based implementations of IDF and PQ indices, and we're working on our own implementations of disk-scanin as well. What this means is that it scales way beyond memory. So one of our power users is in production using a single node to search over 1 billion vectors with low latency. And then we've also spent a lot of time sort of doing hand-coded SIMD for like the distance computations for L2 and dot product and things like that, and also vector compression. All right. So let's spend a couple minutes seeing sort of Lance in action here. And I've got a little notebook to prepare. Hopefully the font is big enough for everybody. Yeah, can you guys in the back see? Okay, great. So I've already installed everything. So essentially what we're going to do is just build a quick question and answer bot with sort of a data set that I've downloaded. And basically this is a data set of YouTube video transcripts, and we're gonna use it to answer a bunch of questions. And it's important that we use this data set so we prevent our LLM from just hallucinating random answers. So we're gonna use Hugging Face to get this data set. And you can see there's 208 rows, and there's a bunch of titles here. This is about 700 videos roughly. And I guess if you look at the first row, you can kind of see there's a title for that video, the URL, and then this is a text. So it breaks down each sort of row in this data set is like one snippet of text here, and then there's a start and end segment. So this data set in its raw form is actually not super useful because the sentences are so short. If you just give it to these sentences to the embedding API, you're not going to get answers very meaningful. Like you might get like type and that, but then that's about it, right? And so what we're going to do is use Lance to actually roll this together. So I would have preferred to use pandas, but unfortunately, pandas rolling window functions consider text columns nuisance columns. So I have to kind of write my own temporarily. Hopefully we can can contribute back up to pandas. But essentially, this is sort of should feel familiar. We're going to group by the video, and for every video, we're going to roll up every sort of essentially 20 sentences, right, for the text column. And then when we execute that, we can kind of see that the data still looks the same, but the text column is going to be much longer, right? This is 20 sentences kind of, or snippets connected together. So now this is our prepared data set. And then what we're going to do is create an embedding function. Here we're going to use the OpenAI embedding function, Ada 2 embedding model. And then we're going to plug this function into LanceDB. And so in the interest of time, because it takes a while to make all of the API calls, I'm not actually going to call this one and create data. I'm instead just going to open the LanceDB that I have with the data that's already created. There's about 48,000, just under 50,000 rows left over. And now we can use it for retrieval, right? So like here's a question from essentially the tutorial that James Callan has set up. Which training method should I use for sentence transformers when I only have pairs of related sentences? So if you know the answer, you can keep it to yourself and you can verify whether the answer is correct. And so the process that we're going to use is essentially, we're going to call the embedding function on the query, right? And then we're going to execute that one. So we get a huge, I think this is 1,500 dimensions, vector back. And so I guess I should assign that to something. And then what we're going to do is use the table to search for it. Search this embedding, and then it's going to be limit. Let's just look at the top 3 answers, and then I'm going to turn it into a pandas data frame. And I guess this would be like our top context, something like that. Okay, and I get 3 rows back. And basically, these are the top 3 most relevant contexts based on the OpenAI embeddings model. Right? And so you can see the title is Unsupervised Sentence Transformers, Intro to Sentence Embeddings. Sounds pretty relevant, and then sort of the text also seems pretty relevant as well. And so what we're going to do next is we're going to have a little helper function that turns the data that we get back in terms of like video IDs and start ins into an iframe, and we'll use this later. But essentially, you can just kind of see the text that we get back, we output some iframe. Okay, so we have the most relevant documents. Now, how do we answer the question? Of course, with a simple prompt engineering here, we create a little prompt to say, answer the question based on the context below, and this gives us a way to make OpenAI use the information that's in the video rather than just hallucinate its own answers. And then we're going to essentially give this prompt to the DaVinci 3 completion API in OpenAI, and now we can put it all together. So I've got a little radio app. Essentially, you see the same embedding function call and the same search call, and then we're going to take the retrieved context and pass it into the prompt along with the question, and then we're going to complete the prompt, and then using the context that we fetched, not only do we get an answer, we can also show you the video and start it at the right segment to answer that question. So if I run this, I get a little sort of embedded Gradio app here, and I guess I can just say, okay, what was the query that I had? Okay, so I'll just copy paste this in here, and then do submit. And this takes a few seconds. Okay, so we got an answer back that's NLI with multiple negative ranking loss, and then it's a little chopped, but if I hit play here, you can kind of see that it starts at 449 instead of 0, and you sort of see the top data. So the last thing I'll mention is, of course, the Lance data that you see, the Lance table, is very easy to convert into pandas. Right, so you can turn that into a pandas data frame, and then you can also say, sort of use DuckDB to query this data. So I can import DuckDB, and I can say the table, and then query. Oh, enter too soon. I'll get all my emails. Select star from chatbot using sample 5. Right, to df. Okay, and boom, I can run SQL workloads on my vector data set as well. So, all right, that's the little demo that I've had. And we still have a few minutes, so I want to talk about how we actually implement Lance. And this might have to go a little bit faster, but I'll try to stuff as many details in as possible. So what I call the magic behind LanceDB is actually Lance columnar format. So does anyone, so raise your hand if you don't know what Parquet is. Okay, all right. So Parquet is a columnar format where it's kind of like CSV or JSON, just ways of serializing your data, but it serializes the data in columns, so it's very efficient for these queries. Lance columnar format is something that we've been making since last year, and it's designed as an alternative to Parquet for AI. What that means is it has data encodings for fast scans that's useful for training or deep learning data mining, and it's really fast for point queries, which is really useful for debugging your models. And it's got optimizations for deeply nested schemas, which is really useful for like sensor data or like annotations that you have. And these are all things that Parquet doesn't do very well, and Lance does. Lance also comes natively with what we call zero copy version. So if you append a bunch of rows to Lance, we can automatically version it so you can roll back, and we don't have to store duplicate copies. And we support schema evolution as well, so you can add a column without having to copy the rest of the data. We're working on a write-ahead log, so we can support the rapid updates and deletions as well. So the idea is that a lot of folks who are doing deep learning have to have multiple formats for training, for data mining, analytics, and debugging. And instead, with Lance, they can do it all together. And Lance also supports secondary indices for vector search, among other things. And the primary interface to Lance format into the ecosystem is Apache Arrow. So this is how we're able to interface with tools that I just showed you, like Pandas, DuckDB, and also polars. And so right now, everything else works with polars, but fixed size lists is not yet supported in polars. Although Richie has promised me yesterday at dinner that he would add it, because right now the embeddings in LanceDB are expressed as fixed size lists. And we'll have to skip over a bunch of stuff, but essentially, so the encodings, how we achieve performance, follows two very simple design principles. So scan, we want to keep scan performance very similar to Parquet. So we don't want to scan more data than Parquet or C. In point queries, we try to achieve sublinear time complexity for doing point queries. And then any metadata reads will be amortized over multiple iterative queries. And then just updating a lot of the default parameters for storage, modern storage optimization. And the two that we sort of have in mind is a local SSD, so your modern NVMe, and then also object storage like S3. Okay? And how we're able to achieve really fast random access, you can see our benchmark in the blog post that I've linked to. I think the slide will be available later. is the data is laid out different. So in Parquet, if you have like a string array, on disk it's offset data, offset data, offset data. Whereas Lance, all the offsets are up front, so you can read all the offsets at once. And then for random access, we know exactly the row, the byte range you need to read. And then the metadata, so the time it takes to read the offset is amortized over all of the different random access to take cache. All right, and then the last thing is, I'll mention is the versioning and schema evolution here. So you can see in here we've done 3 operations. So V1 has files 1, 2, and 3, has its own schema, and then we've added a column in V2, and these are stored in separate files. And then in V3, we would add another column but drop C3, and dropping it doesn't mean deleting the files, it means just kind of removing it from the schema manifest. So all the data is still there. There's no duplication in terms of how we store the data. And then each version has a manifest file that tracks all of the columns and all of the whole schema that's available to it. And so this provides us with really fast version checkout. You don't have to like recombine a bunch of things across different versions. And we also support rich commit messages, so you can use it for like lineage and commit tracking. And then one thing that we're super interested in is lazy column materialization, where you can say maybe column 4 is column 1 squared or something like that. And what we'd love to be able to do is serialize on disk just a representation of maybe like a substrate intermediate representation to say plus squared and a source column, but not actually have to store the data. So this would be super efficient for large data sets. All right, we're early product, so I'd love for you to get on GitHub, try it out, tell us how we suck, give us some feedback, feature requests. If you do like us, please give us a star on GitHub. And today and tomorrow I'll be roaming the halls. If anybody wants to hack on something or want to have a session on vector databases or something. All right. Do we have time for questions?
Yeah.
Oh, cool. Oh, cool. I thought it was like maybe 3 minutes left. Okay. All right. Well, if anybody have questions, I can use that time to go back and talk in more detail.
So thank you for the introduction to LanceDB. At the very beginning, you mentioned the problems of scaling the Elasticsearch cluster. Could you please elaborate a bit on that and how that compares to LanceDB?
Yep.
Scaling.
Yeah.
Scaling.
So Elasticsearch. So there's a couple of things. One is Elasticsearch itself actually just uses brute force scanning. So there's AWS has a OpenSearch fork that they've added HNSW to. And HNSW is in memory, right? So then you're sort of limited in how much you would need per sort of level of infrastructure.
But cluster of nodes.
So HNSW is not designed as a distributed index, for example. And then also the cluster is not, like the way that you create a cluster and the way that you shard data is optimized for Lucene and not for vector search or not for like a graphic index like HNSW. So like quickly you would be forced to scan a lot more data than you need to do.
During the demo, maybe I missed that part, but when you collected the context based on your query, was that done by the LanceDB or was it done by the OpenAI?
Oh, collecting the context was done by LanceDB. So, if we come back up here, so the OpenAI, what OpenAI gives us is the embedding. So we take the question, give it to OpenAI, and OpenAI gives us, for Ada 2 gives us like 1536 or something dimensional vector. That's the embedding. And then we use the embedding to query LanceDB to say, find me the top 3 most relevant contexts.
Sorry guys, we're out of time.